Recording now. All right. Cool. How's everybody doing? Let's see some thumbs ups. All right, good. So yeah, well, it's nice that we're able to do the Zoom as another alternative to the normal style lectures. I teach this pretty similar to the way I do in class. So we'll have like a virtual whiteboard pretty much, and I would just take notes the same way you do, and it won't seem different at all. We're entering chapter 5 now, which is stereochemistry. It's kind of a tough chapter, but we can do this. All right, cool. So it's recording. All right, so I just gotta finish chapter 4. It'll take like 2 seconds. Recording now. So what I'm gonna do is jump to my other webcam. There's my whiteboard. It's a piece of paper. Okay, so end of chapter 4. What was chapter 4 about? Cycloalkanes. If you guys have questions, either try chatting or just blurt it out, and I'll get back to you, or I'll answer it. We were on number 8, which was larger cycloalkanes. And that was, when I say larger, I mean kind of like C7, C8, C9, etc., just larger in general than 6, because C6 was our kind of standard cyclohexane, right? We most of the chapter was about cyclohexane, which was 6-member rings. We mostly did this already, so number 8. But the one thing, you know, we also did this. We talked about like why C8, which is cyclooctane, why it has a little bit of strain, and that was like 1.3 kilocalories per mole per CH2, basically. So that's a noticeable amount of strain. What was the rationale? It was 2 words, I think. Anybody remember the 2 words? And those 2 dots will help you remember, right? The 2 dots. You can chat it. Anybody know? Something, yeah, there we go. I see it. Transannular strain. Transannular strain, which basically means strain across the ring. So this CH2 and this CH2 are kind of bumping into each other, and it gives a little bit of unhappiness, and that's expressed in the 1.3 kilocalories per mole per CH2. All right, cool. That was it for number 9. I think there was a table or a chart or figure in page 149, I think, which is about this. I think that page number is right. It kind of shows this type of strain a little bit also. Okay. All right. Number 9 is polycyclic alkanes. Polycyclic alkanes, in brief. Super cool topic, but we're going to barely touch on it. Let's imagine 2 cyclohexanes, kind of like two rings, 6-member rings, yeah, that are fused together. Fused. What does fused mean? Kind of attached, right? So there's kind of 2 ways you can draw this. I'm going to draw. like this. Okay, there we go. That's what I mean. It's a fused cycloalkane or fused cyclohexane, right? It's like, but it's really not. It's not like 2 times 6 carbons. It's actually 2 times. It's actually 6 plus 4 is 10 carbons total. And let's draw a little bit of the wedges and dashes of the 2 CHs. Okay. And okay, is that cis or trans? Chat it. The H's. Yeah, somebody said trans. Yeah, it's totally trans. Yeah, and it's trans, and there's actually a name for this weird thing. It's called decalin. Whoops, DECA. Transdecalin. What is the 10 or do you see deca? How many carbons is deca? Maybe 10? Well, yeah, there's 6 plus 4 is 10. So that's kind of where the name comes from. Okay. And what's the opposite of trans? Chat it. Cis. That's right. So let's draw the cis version of this also. Okay, you can imagine that we'd have 2 hydrogens and they'd be cis. So they are maybe wedge and wedge, right? And the name of this is called cisdecalin. All right, those are pretty easy to draw. Any question about this or no? Otherwise, mute. There's a mute button. I'm not going to go mute everybody, but yeah, okay, so that's cool, right? Now let's draw them. Let's try drawing these in 3-dimensional form, okay? So this one, left one's really easy because now you guys are experts at drawing chairs, right? So to draw the left one, start with a chair, practice your chair. You can draw it bigger. I'm a little limited on space, so I draw it small. Imagine doing it again now. So remember how we have these 2 parallel lines? Well, imagine another parallel line. Just do this. See that? And then we can go doink, doink. Kind of like that. That's transdecalin. That's easy, right? Easy-ish. If you can draw one, you can draw another, right? They're fused like this, okay? And the up and the CHs, that's actually drawn a little terrible. Let's fix it. Because I like to have kind of 2 sets or 3 sets of parallel lines, right? Kind of like this, this. There we go. A little better. A little better. Yeah, a little better. Okay, we're cool. That's transdecalin, yeah? Now, how do we represent the 2 CHs? Well, we're going to assume the wedged one is kind of going up and the dot, dot, dot one is going down. So where are they? Let's draw those H's. Well, one's going straight up, axial. One's going straight down, also axial. Not that bad, right? That's pretty easy to draw. It's pretty easy to draw transdecalin, okay? Let's try cisdecalin now. Actually, before I draw it, any guess which one of these might be more stable? Cis or trans? I don't know. Like somebody said cis, somebody said trans. Probably trans because things are maybe further away from each other. Maybe. Okay. So yeah, cisdecalin is also a little more challenging to draw, but let's do it. All right. So I'm going to draw kind of the right ring first. I'm just going to draw a little cyclohexane. I'm doing terrible right now. Let's try again. That's what I get for taking shortcuts. Let's draw. Cool. All right. All right. There's a reasonable cyclohexane. Okay. Now to draw. Now I'm assuming I drew the right side one. Now, how do we draw this with the cis fusion? It's a little bit challenging. So don't panic. The trick is going to be start with an axial downward thing. Okay. That's not an H, it's a carbon. Okay. Start with that. Everybody cool? Now I'm going to draw my down equatorial thing. That's also a carbon. All right. Everybody all right? Now I'm going to draw kind of like a downward looking thing like this. And then it gets a little weird. It sort of goes like this and that. You can always watch this video later and follow how I'm doing it. But yeah, that's it. That's cis-decalin, right? Okay. And where's my two H's? They're both, you know, in this orientation, they're both going up. So one is very obvious right there, right? H. And the other is obvious, is kind of, it's sort of up in equatorial, it's right there. That's cis-decalin, okay? Based on easiness to draw, which is the easier one to draw, probably that one. I'd say that's pretty easy to draw. This is a little more challenging to draw. These have wound up in my exams, so you might practice these a little bit. And as we get closer to the exam, you might practice your decalins. You'll also see it on the sample exam, so it won't, you know, you can practice it on the sample exam too. Okay, all right. Here's a question. Can they flip? Can they flip the way that cyclohexane can flip? Any guesses? Yes or no? So the fused ring systems cannot flip because they're locked. There's actually one ring locks the other. You know, they're both locked in a way that flipping is impossible. It's just like there's a little lock going on here, and it's also locked here. These are not flippable, so the answer is no. It's not like a normal cyclohexane that can flip readily. Okay. These are also the basis of these decalin type things, are the basis of steroids, which are like growth hormones. They're used in kind of growth regulation, sex hormones, etc. Let's draw one for fun. What do steroids look like? I'm sure you've seen a steroid or two in your biology or something. What do they look like? A steroid. Steroids have this kind of general structure. So I got a little bit of space. So I'm going to use it up. All right. So it's a 6-member ring. All right. Another 6-member ring. Another 6-member ring, but the next one's kind of upward. So we have 6, 6, 6, like that. And then we got a 5-member ring. 6, 6, 6, 5. Okay. And the one I'm going to draw has a little bit more to it. There's a CH3 coming upward, H3C or CH3, right? I'm trying to be bound to the carbon. That's why I wrote H3C. Hydroxy group. This one has a hydroxy group wedged going towards us. It has another CH3 up top. Again, I'm writing H3C so that it's very clearly carbon to carbon bound, right? What's this weird functional group up top? What's that called? Anybody remember from your exam one?
Ketone?
Ketone, that's right. Yeah, it's a ketone functional group, right? Okay, and the name of this molecule is epi-androsterone. Epi-androsterone. This one's used in biology for like development of masculine sex characteristics. as just an example of these. You know, there's tons of steroids that are all involved in like developmental biology. Invertebrates. Okay, cool. So you're going to see more steroids in your biology courses and stuff, and now you know kind of the general structure. But can we draw it in this same scary way as shown here? Yeah, we can. It's kind of fun. So we can actually turn this into a three-dimensional looking structure. How is it going to look? I recommend let's start on the left. And also there's an H here. There's an H there. So this fusion is a sister trans with the methyl and the H. That's trans. So it's going to kind of look like our transdecalon, right? This, and we can start this and it'll look kind of similar to the transdecalon. Okay, you won't have to do this on the exam, but it's just still kind of fun. So this it looks like this. All right, so start with our first cyclohexane on the left. Then we have a trans-linked one. Those two. Sometimes people call these the A, B, C, and D rings. Okay, so this is our A ring and our B ring. Okay, so then we have another one. Looks like that. Then we got our 5-member ring here. 5-member rings, remember, they don't have nice chairs. They have kind of weird. Anybody remember the 5-member ring conformation is called? Kind of envelope, I think we called it. Envelope. Anyway, yeah, but that's cool. We can draw this. Where's all the stuff now? We can draw the OH right here. Up in equatorial. We have the CH3 going up here. That H is going down. Why? What does the 3 lines? Yeah, this is. Yeah, what do the 3 lines mean? It means an alkyne. I'm just kidding. No, alkynes were a 3-member triple bond, right? Now this is. I guess I learned this in math, like equivalent. So this is equivalent to that. Yeah. So I do that frequently. 3 lines is equivalent. Okay. Yeah, what else? We got a ketone up top right here. Sorry, methyl. Yeah, okay, anyway, that's all I want to show. Is this like a kind of a pseudo 3-dimensional structure of this. And I'm kind of skipping some things, but yeah, that's a reasonable rendition of how it looks 3-dimensionally. And it's also it's not very flat. I mean, the chairs are kind of flat structure. The book has a cool figure. I'm going to show the cool figure in the book real quick. Any other questions? Uh-oh. Everybody see my thing? Is it image? Is it sharing? I can't see the chat. I see a thumb. Okay, good. Yeah, so this just kind of shows the sort of how the 2-dimensional structure gets converted to potential 3-dimensional structure, and also how a computer rendition of this molecule looks in 3-dimensional space, which is pretty cool. All right. Anyway, I think that's it for the chapter.
So that drawing that's on top right there, that pentane looks different than what we drew. Is it?
Yeah,
does it matter?
That's a great point. Yeah, because the others are 6-member rings. 6-member rings have a nice chair, right? And 5-member rings don't. So 5-member rings have these weird envelope. I think we showed the space shuttle conformation. It looks like an airplane. Uh-oh, dog alert. Yeah, anyway. Yes, so 5-member rings have this kind of weird looking shape. 6-member rings are easier to draw for us because it's just a chair, right? So yeah, that's cool, isn't it? And yeah, okay, great. So whose dog was that? Okay, cool. Back to the page. All right, so we're back here now.
Do we always label from left and right?
Left and right. What are we talking about?
Wait, can you hear me?
Yeah, now it's better.
Oh, do we always label from,
Okay.
sorry, do we always label from left to right for the,
Oh yeah, you know, steroids, yes, always. It's you traditionally always go from left to right in a steroid, yeah.
okay.
I always draw it 6, 6, 6, 5. That's just the way you do it. Yeah.
Okay, thank you.
Yeah, it's a standard nomenclature. It would be really weird to draw a steroid like right to left or backwards. Yeah, I know nobody would know what you're talking about. But
Okay.
steroids traditionally always have that kind of arrangement, we'll say. Okay, cool.
Okay, thank you.
All right, here we are, chapter 5. Stereoisomers. Stereochemistry. So this is kind of what, you know, when we're talking about the little wedges and the dashes, that's kind of an example of stereoisomerism and stereochemistry. So it has to do with the three-dimensional arrangement of atoms. Somebody said, do all steroids have the same layout? Are any new ones being discovered? That's an interesting question. Okay, so it's a two-part question. It's in the chat. Do the steroids have the same layout? And the answer is generally yes. I mean, there's some novel steroids that might be a little more complicated, but like masculine and feminine steroids, they kind of have a similar structure. I mean, you can look up you can Google or Wikipedia like estrogen and estradiol. Those are like usually used in female sexual characteristics and you know, as growth hormones. Yeah, they also have a 6, 6, 6, and 5, but they have differences. So, and those are all kind of recognized by our bodies. And they lead to different sexual characteristics. The other question was, are any new ones being discovered? That one, you know, we've been studying steroids for 100 years more, maybe 100 and many. I don't even know when they started being discovered, but we have. I don't really know about like new steroids, like at least in humans being discovered, because we know all the common structures pretty well. Maybe in like there may be steroid-like structures in maybe like marine organisms, or you know, in the bottom of the ocean, that are unique. And yeah, those are probably, yeah, those would be new steroid-like molecules being discovered. But yeah, they're a very interesting class of molecules, right? And kind of fun to, I mean, I like looking at the differences between different molecules, including steroids. And yeah, cool. All right, so let's get into chapter 5 now. Okay, so first, usually I'm at a whiteboard and I'm looking at you, but right now I'm not. Let's consider my hand and your hands. Okay, so I'm gonna first draw horrible pictures of hands. There's my left hand. There's my right hand. And I mean, think about your hands, right? Are they the same? Well, yeah, kind of, but they're not like, are they superimposable? Can I put one hand on top of the other hand and have it be the same? The answer is no. I mean, what's a good word to describe the relationship of our hands? Are they,
Mirrored.
was that?
Would you say mirrored?
Yeah, mirror, good word, yeah. Yeah, they're mirror images. My left hand and my right hand are mirror images, right? And we're going to see the same thing with molecules, that relationship of mirror images, right? So yes, they're mirrors. You've probably heard little bits of stereochemistry earlier in your chemistry courses, but this will be a little more of a more detailed treatment. Yeah, they're mirror images, right? Then maybe we'll say, not only are they mirror images, but are they superimposable mirror images or non-superimposable? Meaning everything has a mirror image, right? Everything, like, right? Like a pencil has a mirror image, right? I don't know, here's a pencil. It's a really ugly pencil, but it has a mirror image, right? And let's just imagine all the yellow is very consistent around it. I mean, this would have a mirror image. I don't know, a second pencil. Let's pretend these are mirror images of each other, right? We would say they're probably superimposable mirror images, right? So if I superimpose this on top of the other one, it's like they're exactly the same, right? Right? I'm assuming there's no text. Ignore the text on these. Just a yellow pencil. Yeah, these would be superimposable mirror images. But your hands are also mirror images, but they're non-superimposable. Meaning if I superimpose my two mirror image hands, they're different, right? They're non-superimposable, right? And I can see that if I put my hands together, yeah, they're if I try to superimpose them on each other, it doesn't work, right? Molecules will also have that possibility of being mirror images, but non-superimposable. All right, cool. Let's also review isomers. Remember isomers? Different kinds of isomers. What are our different kinds of isomers? What's the one we've been kind of talking about recently? Chapter 4. Yeah, somebody said circles. Yeah, circles would be superimposable mirror images, right? So somebody said in the chat, like, if I draw a circle and I draw a mirror image of that circle, those would be superimposable mirror images. Yeah, right. Okay, so what's the kind of isomer we've been talking about recently in chapter 4? Name of it? Constitutional. That's right. Constitutional, also called structural. Okay, so these have the same molecular formula, but different connectivity. And I think a good example is C5H12. Which is cyclic or acyclic? It's acyclic because we have 2 times 5 plus 2 is 12, right? And the extra is 2 suggests it's acyclic, right? And if we can draw these real quick, we've done this a few times now. 5 carbons, 1, 2, 3, 4, 5. And then we could do like 4 carbons with a methyl there. We could do 3 carbons with 2 methyls. I think those are the ones. Yeah, cool. All right. So and we also did introduce the word stereoisomer, right? What was a stereoisomer? Example of stereoisomers. Maybe what, like cis and trans, right? That cis and trans on a cycloalkane. Like we did this early chapter 4. This is cis, CIS, and the alternative stereoisomer is trans, right? Okay, yeah. So so what defines a stereoisomer is same connectivity, right? Here it was different connectivity. Now it's the same connectivity, but what? But different what? Different, how do you describe the, somebody said it, yeah, spatial orientation. That's a good way to say it. It's like the spatial orientation is different. Yeah, that's a great way to say it. I like to say different three-dimensional orientation, like 3D orientation. That's another way to say it also. Spatial, 3D, all those are same ways to say it. So that's the concept of what a stereoisomer is, okay? Okay, great. So let's keep going. Now, let's describe something called mirror image isomerism. Mirror image isomerism and a concept called chirality. Chirality, C-H-I-R-A-L-I-T-Y, chirality, okay? What do we mean by this? Let's draw a molecule as an example of this. So this is a type of stereoisomerism, okay? Let's draw an example of this. CH3, we're going off to a carbon and an H. Whoa. And let's draw two different things off the carbon. One that's coming towards us, Cl, and then one that's going away from us, Br. Okay. All right, so this molecule let's just think about this a little bit, right? We have how many different things are on the carbon, like unique different things, right? We have how many different things are on the carbon? Well, it looks like there's 4 different things, right? We have a CH3, an H, a Cl, and a Br, okay? And so that kind of, having 4 different things on the molecule or on this carbon will give this a certain special properties, I guess. And let's compare this with a different molecule. Okay, and this is another thing I want to mention right now. Okay, wait. Question: can you show the last page again, real quick? Yeah, somebody said, can I show the last page again? Yeah, let's do that. Okay, so this is the bottom of the last page. Okay, so we're talking about constitutional isomers, same molecular formula, different connectivity. And then we talked about stereoisomers, and these are an example of stereoisomers. So these things are, we have the cis one and the trans one. Cis one and the trans one, okay. Which are same connectivity but different 3D orientation. Okay. All right. Okay. And then somebody also asked, does the symmetry matter when determining cis or trans? Or does it matter if the triangle dashes are different to determine whether they are cis or trans? Well, there's a lot to that question. Some of that I'm gonna have to answer a little bit later, just because it's gonna be easier once you know a little bit more, right? We're kind of early on in this process. But I will say, is there another way we can draw cis or trans, right? Is there another way I could draw cis and have it be cis? Yeah, I could just be like, well, that's cis also, right? These are both cis because the things are in the same relative orientation, right? I could also draw a trans one where it's like dash, dash, dash on top and a wedge on the bottom. And that would also be trans, right? So I could draw, there's almost like two ways I can draw cis. There's two ways I can draw trans. Cis is cis, trans is trans, right? Cis means same orientation, trans means opposite. That's all it means, okay? Okay, all right. So let's keep going now. So look at this molecule, all right? I'm going to draw, one more thing about this. Let's mention this right off the bat. Is this chlorine a little bit to the left and the bromine a little bit to the right? It looks like that, right? It looks like the chlorine's a little bit to the left, the bromine's a little bit on the right. But that's misleading, okay? You should think about this as the chlorine is coming straight towards us, the Br is going straight away. I can't, of course I can't draw that exactly. It looks like left, a little bit left, a little bit to the right, but that will be misleading. Just think about it as towards us, away from us, and that's better, right? Because let me show a contrasting molecule real quick. CH. What if I drew this? What is the relationship of these two molecules? Is there any difference? I mean, it looks like, oh yeah, left, right, and this is like right, left. And somebody said the correct answer, that these are the same. These are identical. There's nothing different about these. There's nothing different. That little left, right, left, right, and right, left, that's irrelevant. That means nothing at all. Nothing, 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 okay? Totally irrelevant. These are identical molecules, okay? All right, how do I draw identical? Like that. Okay, so these are the same, right? All right. I just drew them in a slightly different orientation, okay? All right, so now let's try this in a different manner. Let's draw H3C, CH, and I'm gonna have a little arrow with a question mark. It looks like a resonance arrow, but I don't want to suggest resonance. This has nothing to do with resonance. Okay, and I'm gonna draw Br Cl. Okay. So are these the same? I mean, it looks like some parts are the same. CH3, CH3, HH, but the difference is maybe the Cl is going towards us, the Br is going away. Br is going towards us, Cl is going away. That's a difference, right? That's an actual difference. Okay, so I'm holding two things constant. Like these are constant, and then I'm kind of assuming one thing's, we take this and flip it basically. So now Br is coming towards us, Cl is going away, right? So what's the relationship of these two molecules? And I'm gonna say, what's the relationship? And we just said it a few seconds ago. It was a something, 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 right? It was a, they look, because we're trying to superimpose them right now. Imagine that, try to superimpose this on this. They're non-superimposable, right? They're non-superimposable mirror images. Non-superimposable mirror images. That's the relationship of these two molecules. Of course, if what's the relationship between this and this? Well, they're also non-superimposable. These are the same. So any relationship between these two also applies to these two, right? So these are non-superimposable mirror images. Of course, that one is also. I am going to put this in parentheses because it's all I wanted to do is say that these are the same. Okay, but these are non-superimposable mirror images, right? All right.
The question is, sorry, is that a question mark?
Yeah, what I was, the little question mark. I was trying
Yeah.
to say, what is the relationship?
Oh, okay.
And the answer is non-superimposable mirror images. All right.
Okay.
Okay. Also, any molecule that is has a non-superimposable mirror image, these are a great example of that, are also called chiral. Chiral is any molecule that has a non-superimposable mirror image is also called chiral. Does anybody know what the opposite of chiral is? There's chiral, and the opposite is, let's see if something has achiral. Chiral is this. Chiral always implies the presence of a non-superimposable mirror image. The opposite is called achiral. Achiral means there's absolutely no non-superimposable mirror image. Okay. All right. So it's chiral and achiral. All right, good. One second.
Wait, achiral is superimposable mirror image?
Yeah, that's another way to say it.
Yeah.
Achiral would suggest the molecule has a superimposable mirror image. Yeah.
Okay.
Whereas chiral suggests it has a non-superimposable mirror image. And we'll show us a bunch of examples of chiral and achiral in a little bit.
Okay.
I have little models of these pre-made. Let's see if this works. Let's see if I can do this right. All right, so that actually that's the wrong one. Let's see. So I'm trying to show here. This doesn't work too well with the webcam, but you can kind of see that this what I made here kind of shows that molecule, right? So I'm drawing my CH3 is on the left, right? That's a CH3. I'm just calling this a CH3. All right. We have a CH3. There's my H, which is a little white thing. Br is going away, and the chlorine's coming towards us, right? The green's the chlorine. All right. See that? So that is the left molecule. Okay. How do I actually let's make it a little more like, see how the chlorine's a little bit to the left and the bromine looks like it's a little bit to the right. See what I did? What if I do this? Well, it's the same molecule, and that's what the bottom one is, right? The bottom one has the chlorine being shown a little bit to the right and the bromine a little bit to the left. But of course, they're the same thing. I'm just looking at it from a slightly different angle. So top, bottom, right? Wait. Top, and the bottom, they're the same thing, right? I'm just rotating it a little bit. Okay, somebody said, just to clarify, the top two are superimposable, and the bottom, that's okay. So somebody asked to clarify, the top two are superimposable. No, the top two are non-superimposable. Let's ignore the bottom one right there. These two, I'm saying these two molecules are non-superimposable mirror images, right? These are non-superimposable. And it's not impossible. It's not the word, I'm not trying to say impossible. It's one S, it's imposable, superimposable, meaning they can't be put on top of each other. These are different molecules, right? I was just trying to say, these are the same thing. Just ignore this. Those are the same molecule, just looked at from a slightly different angle, right? If you twist the top a tiny bit, it's this. We're not doing anything, we're just twisting a little bit, right? These are the same, okay? Okay, so this is a model of the left molecules. The left molecules are the same, right? The chlorine is green, the bromine is red, right? Everything cool? Now, what does the model of the right look like? Okay, so now the chlorine's in the back, the bromine's in front, right? See that? See how this and this CH3, that's a CH3, right? That's there on the left. Okay, right? That looks pretty good. What happens if I try to superimpose these on top of each other? It doesn't work. You can't see it too well, but see, I tried to put them on top of each other. Oh no, they can't. Why? Because now things are mismatched, right? That's what we mean by non-superimposable mirror images. I'm trying to superimpose them. It doesn't work. It doesn't work. These are the left and the right, which are my two models, are non-superimposable. Some things are superimposable, like the CH3 is superimposed, the H is superimposed, but the other things, the bromine is red and the green, chlorine is green, they don't superimpose. Okay, all right. So you can do this with your own models as well. This little exercise. Try to make a model of the left, try to make a model of the right, and confirm that they're non-superimposable. And these two are just looked at from a slightly different angle, but they're the same. They're identical. Okay. So what about so I'm going to draw this. I'm going to draw another molecule, and we'll decide if they're the same or different. Okay. So what's the relationship of these two molecules? Are these non-superimposable mirror images, or are they the same molecule?
Same.
They're the same. And this is what I just showed, like the two molecules that are stacked, right? It's the same thing. I just made it a little more profound, the difference. But the clear thing is, yeah, we have a methyl on the left, H on the bottom. Fluorine is coming towards us, bromine's away. Fluorine's coming towards us, bromine's away. But again, the fact that the fluorine looks a little to the left and bromine looks a little to the right versus fluorine a little on the right, bromine on the left is irrelevant. These are the same molecule, same. They're the same. Are these chiral or achiral? Just because I drew the same molecule doesn't mean they're not chiral. And the answer is they're totally chiral. It's just I drew the two copies of the same thing. I just slight different orientation, right? I took this, I took this, I twisted it a bit, and it became that, right? Took this, twisted a bit, and this became that. These are the same molecule, but they are chiral. They are chiral. And what does chiral require? Okay, so somebody said, I thought chirals were non-superimposable. That's a great question, or that's a great statement. The statement was, I thought chirals were non-superimposable. Okay, but the thing is, so chiral is not in a relationship. I'm not saying like these are like, I'm not describing the relationship between these two molecules, because the relationship of these two molecules is the same. Chiral though means that there is a non-superimposable mirror image, that there is. It's an adjective, right? It's a property, right? Chiral means there is a non-superimposable mirror image. I'm just not showing it here. What would it look like though? These are both the same molecule, right? What would the non-superimposable mirror image be? Because if it is chiral, it has it. What would it look like? So, we'll say, for example, for example, what would it look like? I would just have the bromine coming towards us and the fluorine going away. So that non-superimposable mirror image would look like this: H3C, H. Cool. All right. And well, sorry, I can't zoom. I can't unzoom, sadly. Okay, but yeah, fluorine will go away now, and the bromine will come towards us. BRF. Okay, yeah, good. All right. So do you see now how this is the non-superimposable mirror image of that? The fluorine was coming towards us, bromine was going away. With the non-superimposable mirror image, the bromine is coming towards us and the fluorine is going away. Okay. All right, good. And we'll give you a nice, easy name for that relationship in a second. All right, good. Good. Any questions on this? Let's move forward and we'll start giving you some definitions and it'll be a little easier. Okay. All right. Okay. Okay, so we're on to number 1, chiral molecules. Everything until now is kind of introductory, but it's kind of getting us in the right direction. Chiral molecules definition. A chiral molecule is a molecule that is not superimposable So not superimpossible, but superimposable on its mirror image. That's a direct definition of the word chiral. Okay, a molecule is not superimposable on its mirror image. Whoa, and you could say that it's an adjective. An adjective, so it's a property. Okay, it typically requires an sp3 carbon. sp3 carbon with how many unique substituents? Give me a number. How many unique substituents? 4. That's right. Somebody said 4. Yeah, with 4 unique substituents. That's going to be a requirement. Generally, there's a couple exceptions to this, but for you guys, 4 unique substituents is a good, simple requirement. So let's draw another example. H. C, F, Br, Cl, Br. So we have 4 things. Why does it have to be carbon? And somebody said maybe because it's an organic chemistry class. That's a good point. Yeah, what does it have to be carbon? And somebody said maybe because it's organic chemistry class. Well, that's actually really interesting. For the most part, for you guys, it will always be carbon. But does that mean that there's ever a case where non-carbon can be chiral? Or yeah, non-carbon can be chiral. And the answer is yes, you can have non-carbon atoms, but the requirement still is 4 unique things. Okay, that's a general rule. Without getting into detail, because we're a little low on time, yes, like sulfur can be chiral, nitrogen can be chiral, and I'll totally talk about that maybe in office hours or something if you want to come. But for now, for you guys, carbon. Yeah, good, great questions. Okay, so this is chiral or not? I mean, it looks like we have 4 unique things, so probably chiral, right? Probably going to be chiral, right? Okay, and if it is chiral and it has a non-superimposable mirror image, then we should be able to draw that. And I'm going to do that. And I'm going to, there's multiple ways for us to draw this mirror, non-superimposable mirror image. There's multiple ways. Let's draw, I'm going to draw it a different way. And I'm also going to have my little arrow. I mean, yeah, my kind of like a resonance arrow. And I'm going to write EN. EN, we'll get to EN in a second. I'll tell you what it means, but it basically refers to a non-superimposable mirror image. EN is an enantiomer. So we'll formally define that in a bit, but that's what we mean. An enantiomer is a non-superimposable mirror image. Let's draw it, because in the last page, I would usually just have these two down there and then just flip the other two, right? Right? I'd keep these sort of the same and flip the others. Let's just think about another way to draw a mirror image, because there's multiple ways to draw a mirror image. What if I draw the fluorine coming, like, imagine we have a mirror right here. This is a little mirror. Like you're this molecule, you're looking at the mirror, and it's kind of hard to envision what I'm trying to do, but let me just do it. All right. Okay, so what if I just imagine like if there's a mirror, what would both of these molecules look like if they are mirror images? Fluorine would be coming towards the mirror, and the hydrogen would be going away from the mirror, right? And now the chlorine is coming towards us, and the bromine's going away. Because we're imagining kind of, let's pretend we're standing right here. We're standing right here. We're looking at this thing. We're looking at the molecule, like we're in the plane of the carbon. You know, from our position. Let's even do this. Let's draw the little person a little bit lower here. Okay, so okay, you know, they're looking at that carbon. Imagine there's a mirror right here, right? What they would see from this perspective, assuming there's like a mirror here, like a mirror, like there's a mirror. What would this person see? Well, in the, you know, as they're looking at the mirror, the fluorine would be kind of closer, and the hydrogen would be further, because that's the way your mirror works, right? But from their perspective, the chlorine is still to the left, their right, and the bromine is to their left. Okay, so this is a way to draw these two things. That's one way. I'm going to get rid of the mirror now. Okay, because I'm trying to point out there's multiple ways to show this relationship. These are definitely non-superimposable mirror images. Okay. Another way to draw the mirror image to really prove that these are not the same molecule, right? How's another way I can draw this? What if I take this? Now I'm going to take this molecule on the right, take it and flip it over. Okay, right? Take it, pull it up, flip it over. What's it going to look like? Take it, lift it out of the page, flip it over. What's it going to look like now? We're not changing it, we're just flipping it over, right? So it looks like, let's draw our C in the middle. I take it, I flip it over. Now the fluorine's on the right and the hydrogen's on the left, right? Because I claim these are not the same molecule. And if they're not the same molecule, if I take this and flip it over, it's still not the same, right? These are not the same, and these will not be the same. But what happens now if I take this, flip it over, take it out, flip it over? The chlorine, it was going towards us. Now where's the chlorine? It'll be going away, right? Took it and flip it over. Now the chlorine's going away, and where's the bromine? The bromine was going away. Now the bromine is coming towards us, right? So these are the same molecule, right? Top and the bottom are the same. Can you now also convince yourself that these are also not the, like if I look at these two molecules, are they, what's their relationship? They're also non-superimposable mirror images, right? Okay, so these are non-superimposable mirror images. These are the same. So of course, this versus this, that's also a non-superimposable mirror image. Do you see that? Do you see how they're definitely not the same, and how they might be a non-superimposable mirror image, right? Because you try to superimpose this on that, and they're obviously not the same, right? Okay. And what's this? What do you think the definition of enantiomer is? Like, these are enantiomers. What's a good definition of the word enantiomer? Maybe non-superimposable mirror image, right? Enantiomer means non-superimposable mirror image, which these are. Okay. All right. Good. Let's try another one. So we're still on number one, chiral molecules. Number one, chiral molecules. Continuing. All right, let's look at another example of this. Let's draw CH3, CH2, carbon, CH3. Let's make a hydroxy group, alcohol. Okay. Chiral or not? Any predictions? Okay, somebody asked a great question in the chat. Somebody asked, wait, did you say enantiomer is achiral or chiral? So that's what they asked. Did I say that enantiomer is achiral or chiral? Okay, so enantiomer is a different concept. So enantiomer is a relationship, right? I can say, like, yeah, these are enantiomers. It's a relationship, right? Chiral is a adjective. It's like, it's a property. So I can look at any molecule. I can just say, hey, is that molecule chiral or achiral, right? So that's different. Chiral means presence of a non-superimposable mirror image, right? I can look at that molecule and say, that's a chiral molecule. It has a non-superimposable mirror image. And what do you think that non-superimposable mirror image looks like? Aha, there it is, right? So that's chiral and that's chiral.
So,
and they are enantiomers.
Okay, so if a molecule is a chiral molecule, that means that it has one or more enantiomers?
Only one. You can't have more. You can't have two. It's impossible.
Okay. So
well, what about these? You could say, oh, this has two enantiomers, but no, these are the same. You can only have one enantiomer, right?
Okay.
These are just different ways of showing the same exact thing, right?
Okay.
I flipped them over, but it's the same molecule. Okay.
Okay. So a chiral molecule has an enantiomer.
Always.
That's always. That's like a fact. Okay.
Never an exception to that. A chiral molecule, every chiral molecule has an enantiomer. Yes.
Okay. And an achiral molecule does not have any enantiomers.
Always. That's always correct. An achiral molecule can't. Yeah. If you think about an achiral molecule, we'll see that in a second. That means its mirror image is superimposable, and so That
Okay.
makes it not an enantiomer. Okay. All right, good. Cool. Let's look at this molecule. So is it chiral? And answer is probably yes, because we have a carbon with 4 things on it, right? OHH, CH3. You can say OHH, a methyl, and an ethyl. That's an ethyl, right? So it is chiral, yes. And by being chiral, it has to have an enantiomer. Okay. So what I was just saying a second ago is there's multiple ways we can draw the enantiomer. Okay. So let's try. There's multiple ways we can draw the enantiomer, right? So I like to say resonance looking arrow En for enantiomer. And how am I going to draw the enantiomer of this? Well, one way I can do it is let's pretend we have the mirror again. So we have a mirror. And so the mirror is going to look, the mirror image is going to look like CH3, C, CH2, CH3. So that's kind of like the idea, like I'm standing over here, and I'm looking at this thing through a mirror. It's like, yeah, and as I'm doing that, the hydroxy group is still coming down this way. And the H is going kind of to the opposite way. So these are enantiomers, right? This is the enantiomer of this. They're both chiral. They're both chiral. Yeah. Is there an alternative way to draw the same exact molecule on the right? Yes. I can always flip a molecule around. So imagine what's going to happen if I take this and flop it over. I take it and flip it over. Now the ethyl will be on the right. Methyl will be on the, sorry. Ethyl on the left, methyl on the right. And now the hydroxy, the OH, will be towards us or away from us. If I take it and flop it over, OH is towards us or away from us? Take it.
Away.
It's away. Yeah, now the hydroxy is away. Now you can totally, like, if you compare these two molecules, you can totally see, oh yeah, they're definitely not the same thing, right? Because everything aligns, right? These are aligned, that's aligned, but the hydroxy is coming towards us versus the hydroxy is going away, right? Cool. Yeah, great. What about, so one of the points here is anytime I draw the enantiomer, anytime I draw the enantiomer of a molecule, there's multiple ways to draw it. Now, you might develop your own opinion over the way you like to draw it. I actually like these two. I like these two are a great way to show the enantiomeric relationship because everything's aligned except like, oh, the hydroxy's towards us versus going away, okay? But this is also an equally valid way to draw the enantiomer, okay? Let's show another example. What's the relationship between these two molecules? What's the relationship? And maybe before we can do that, is this chiral? Left one or right one, are they chiral? I mean, it looks like the same connectivity. Chiral or not? Chiral or not? The answer is no. You don't have 4 things, right? Right? So what, okay, right? Yeah, so what's the word for that? It's not chiral, but it's achiral. So then what's the relationship? They look kind of different, right? Maybe, but are they enantiomers? No, remember enantiomer, and I'll totally define these things probably next lecture. Somebody said constitutional. That's a good guess, I guess. Well, not even constitutional because it's the same exact molecule. Take this, flip it over, and what's the, oh, it's the same molecule, right? Take it, pull it out. It's the same molecule. Somebody said, wait, why not chiral? My main requirement for chiral was up here, like 4 unique substituents. Hydroxy, H, ethyl, methyl. Those are 4 different things. Here, it's like I have a CH, these are the same, methyl, methyl, hydroxy, H. So you need at least 4 unique things. This is 3 unique things, right? I have 1, 2, and these are the same, so it's 3, right? Okay. So the relationship is the same, right? And also you could say, another way to say that, this is, I mean, by same, we mean superimposable. So these look like mirror images, but they're superimposable mirror images. Superimposable mirror images. And another way of saying superimposable mirror images is with the same molecule, right? Anytime you have superimposable mirror images, because they kind of look like mirror images, sort of, but they're superimposable on top of each other, that's the same as saying same. These are identical. And again, if you don't believe me, take this, flip it over. Ah, it's the same molecule, right? Okay. And we call it, that's achiral, okay? I'm going to, I have like 2 minutes. I'm going to do like one more real quick one, very quickly, all right? It's all recorded also, if you want to watch it again. So we're just talking about chirality. Let's just draw that molecule. Let's make it a little more. I'm going to move the bromine a little bit to the left. Okay, chiral or achiral? Yep, somebody said chiral. Yeah, of course it's chiral. I have a propyl group on the left, a methyl on the right, a bromine and an H. So yeah, totally chiral. And let's, how can I draw the enantiomer? Because if it is chiral, it always has an enantiomer, right? There's, again, multiple ways we can draw it. I'm gonna just draw the 5-member chain. And one way I can draw it is just be like, okay, well, the BR is still this way. These are the 2 enantiomeric forms, right? They are mirror images of each other. You can see it. Imagine a mirror and like, imagine me looking through the mirror and what do I see? Yeah, it looks like that kind of. But I can also draw it another way. What's the other way I can draw this really easily? I can just imagine, keep it all the same. I keep it all the same, but just imagine the BR going the opposite direction. Right? If you just envision these 2 molecules, you can totally see, yeah, they're enantiomers. These are the same. I'm looking at them from different angles, right? Because what happens if I take this top one and flip it over? Oh, it's the same. It's this, right? Take it, lift it out, flop it over. Yeah, now the bromine will be going away. So these are the same. So these are 2 ways of representing the enantiomer, right? And of course, they are both the same molecule. And they are enantiomeric to this molecule, okay? Okay, so the last thing I'm gonna say, we're done, but let me just give you a name for this concept. What's this thing? What's a good name for this thing? A carbon with 4 things on it. What should I call it? What's a good name for a carbon with 4 things on it? I don't know. What do you think?
Butane.
What's that? Say again.
Butane.
Chiral Center. Somebody said it. Yeah. Chiral center. Chiral center is a good way to say it. It's a carbon with 4 things on it. Chiral center. There's a bunch of other names we'll describe next time. Somebody said meso, and that's not right. I'll talk about meso later. So not meso. Meso is a different concept. So not meso. But chiral center, that's a good one, right? Carbon with 4 things on it. 4 things. So I think that's all we got time for. Are we done? For today, we are done. Hooray, we made it through a little bit of stereochemistry. There's more to learn, but that's a good start. All right, I guess I'll see you guys in class on Thursday. See ya.
Wait, so when you did that whole concept of imagining the paper and flipping it over,
But also,
that's how you
wait.
found-
I'll keep talking for anybody that wants to keep talking to me. But formally, the lecture's over. But yeah, you guys can ask some questions if you want to stick around a bit. Okay, so what was the question?
So when you did the whole concept about imagine flipping the paper over, that's how you find the mirror image of what you're looking for?
So so
Is that the right word for it?
sometimes people have difficulty doing what I was trying to say, or that, imagining there's a mirror, right? So imagining, and I know I understand that's a little weird. I mean, like if I imagine, I don't know, I'm like, if I am looking, I'm looking and I have a table and there's a mirror, right? And I have some object. If I have an object, A, and I'm looking at A, I guess, through the mirror, it's like, what do I see? That's what I'm trying to say. Like if I'm here and I'm looking at this molecule sitting on a table, it's like, what would it look like in a mirror? And it would look like this, right?
Yeah, and also you're right, because oh yeah, I was remembering. Now I'm remembering that the dude, the stick figure on the left, we're imagining that someone's on the left of this looking.
Yeah. It's like, we're like right here. We're like, what do I see? What do I see? I'm looking at that molecule and I'm pretending there's a mirror right here. It would kind of look like this, right? In the mirror, right?
Yeah.
That's what I'm trying to say. It's like, yeah. So, but and that is definitely one way to show this relationship. But this is another way. I like this way, right?
Okay.
Let me even do it a step further. I'm gonna redraw these really easy, really simply up top, right here. Same molecule. Okay.
Okay.
And ignore the hydrogens. If you ignore the hydrogens, it's almost easier. These are enantiomers, right?
Okay.
We're just on the H's, but they're there. And of course, this can be also shown like this, right?
Okay.
And so if I just cover up that top molecule, let me make it a little more dash BR, right? So this is a cool way to show an enantiomeric relationship also. Just draw it identical, 2 identical copies of a molecule, right?
Yeah.
And just have the chiral center be one way or the other. That's a great way to show an enantiomeric relationship, right?
Okay, so
or alternatively, I mean, that's another great way to show an enantiomeric relationship.
Okay.
Both of them are completely correct.
Okay. What about, so what if you just ignore the molecule on the left and you just looked at the top right and the bottom right?
Yeah, you would say those identical. We'll say those are identical molecules.
And they wouldn't be enantiomers, right? Would not?
Because they're identical. Yeah, you can't, if the molecules are identical, they're definitely not enantiomers. I mean, identical means by definition superimposable, right? I can totally superimpose that top one on top of the bottom one. Now, of course, I have to rotate it, but yeah, take the top one, flip it over. It's the same thing as the bottom one, right?
Okay.
Take it, flop it over. Yeah, of course, it's the same, right? So by being the same, they're definitely not enantiomers. Enantiomers are never the same, right?
Oh, okay.
Because same would be another way of saying superimposable, right?
Yeah, okay, I see what you're saying. And you can't flop the left one over to look like the right one.
Absolutely not. Yeah,
I can see it.
That left one is completely you could flop it a million different ways, and it's not that. It's because if molecules are different, you can never flop them in a way that makes them the same, right?
Yeah.
You could spend a
Okay.
million years doing it, and you'll never get that molecule to actually look or to actually fit on top of that molecule. It'd be impossible.
Okay.
You could almost
makes
get it
sense.
to look like, you could get it to look like that, but that's not the same molecule, right?
Yeah. No.
Like that looks almost like that, except for the
Yeah. The
spoon.
poking at you and poking away
Yeah.
from you.
Yeah, I don't know. Does that make sense a little bit?
Yeah. That
Okay,
does
so for
actually.
where we are, I think you got it. These are cool examples, definitely.
Okay,
And then now you have the word chiral center. That's a great way to describe a carbon with 4 things on it.
Chiral Center carbon with 4 things on it.
All right, you cool?
Sounds good. Thank you.
All right, see you Thursday.
Bye.
Bye.